My story starts in October 2023. We got a call from GRW in Worcester. They asked us if we would like to design the largest FSW machine in Africa, and some might even say in the Southern Hemisphere. It's a 12.5 meter long friction stir welding machine to weld the barrels of their exported tipping silo trailers. They asked if we had appetite for such a project. Of course, we said yes. We love a challenge, and this surely was a challenge. So there we were, 3 mechanical design engineers, 3 electrical engineers, 2 project engineers, and 2 technicians. We had built a similar machine back in the 2000s, but this one was on another level. Over the next 16 months, we would have to conceptualize, calculate, design, and manufacture the machine for this. We did do the manufacturing externally, so it wasn't in-house. Our facilities is a little bit small. But first, let's just backtrack a little bit. What is friction stir welding? It is a process that's carried out by plunging a rotating, non-consumable tool in between 2 plates. So on the joint line, on the abutting plate, you plunge the tool and it rotates, and then you drive it forward. And it effectively stirs the material together, creating a really good joint. It's instead of using, say, MIG welding. We did have our challenges though. Whoops, this is going a bit fast. We did have our challenges preventing plate separation, because as that tool is rotating, it wants to push the plates apart. And in our first machine, we had endless headaches to keep the plates together. If it separates just a little bit, the weld is not good enough. And then also, if you weld a barrel, like on the back of a truck, once you fold it over and you weld that joining seam, you have to get that off the machine. So either you can use a cantilever, but the forces required are really high, or you have to have 2, say, ends. But then when you weld it together, how do you get it off the machine? You can't cut it because then you have to weld it again. And also you have to minimize the step between the butting sheets. So both like this, and also between the backing of the machine. And we wanted to increase the weld feed rate, so we had to have ample capacity on our clamp packs. So typically a friction stir welding machine has the following components. It's got a spindle, which is, I don't know if this thing is working properly. Sorry, this way around. It's got a spindle over there, and there's your friction stir welding tool. Then you have your clamp noses, and then your backing plate. For the space fans out there, the Falcon X booster tank is friction stir welded together, and for the petrol heads, the Ford GT center tunnel is friction stir welded to a sheet which houses the fuel tank. We had to come up with some concepts. Back to the story. I had to come up with some concepts, specifically how do we get the barrel on and off the machine, how do we fit in the clamps, where do we put the spindle, how do we fit the tool, how do we remove everything, and the space was tight. Between the clamp noses, there's about 100 mils. We did some calculations. I used SANS 10162 for the calculations of the big beam or the big girder. So if there's any structural engineers here, I'm sure you would have heard of that standard. I also used a book by Jay Mahachi, which is an excellent book, which really does explain it well. I really enjoyed this process. It's not something we learned in undergrad, typically structural engineering things. So it was really good to do it. So after about 35 pages odd of hand calculations, we could move over to more final designs. And this is what we are looking at the moment. So there's the latch, which opens and closes. Then you have the girder, which is your main load-bearing component, and your fixed structure on that side. These are the clamp packs, which actuate, which hold the barrel or the plates together underneath the machine. And then our welding unit sits at the back, and we're welding from underneath. So you have a backing plate, your welding unit, and your clamp packs that clamp that against the backing. And then we have a roller to flatten the 2 plates that are joining. We have a sander to clean the weld on the reversing cycle, and a vacuum unit to suck up the aluminium dust. So I was responsible for the superstructure, so for this component and the fixed structure and the latch, and also worked quite a lot on the clamp packs. And then I helped out on the rest of the components, of course. This is just a dimensional overview of the structure. It weighed, or just those pieces, the girder or the boom and the fixed structure and the latch weighed over 60 tons, so it's not a light structure by any means. And we wanted to do a weld length of at least 12.5 meters. For their tanks are about 12 meters, but we wanted to have some extra room. I'm not going to go into details with all the different components, but if you have any questions, please come and speak to me afterwards. So this video should play. It's just a quick flyby of the machine. Let's check. I say. So we're zooming into the clamp packs there. So there's 10 of them aside, 20. There's the barrel on the top. This is the fixed structure, the electrical cabinet. That's iMic. You may have 4 fingers in the drawing there. Then that's the welding unit. Those are the six sensors. That's the welding tool in the spindle. And now we're going to look down the throat of the machine. That's our hydraulic cylinder to clamp the roller to join to flatten the 2 plates. We have our sander over there, and this is down the throat of the machine. Then we're going to zoom out a little bit. Sorry, it does take a little bit long. You can see some of the civils work underneath here. So the substructure, those are M64 threaded rods. Then that red parts, that's because this whole thing runs on one big linear rail. And we had to, because it's concrete and it's civil work, we had to make sure that we can level that afterwards, because if it's not level, it's not going to work. These are your 2 main lifting cylinders for the latch, your alignment tool, and that's the backing plate, and that's your barrel, and your weld would effectively run along there. Okay. We made drawings. Between the 3 of us, we made around 500 drawings. This is one of the more involved drawings of the spindle housing, which I did for manufacturing. And just a note on that, if you don't communicate well on a piece of paper, the machine will not come out correctly. So you really have to make sure that what you're communicating on the 2D sheet, which is all the person sees in the workshop, does convey what you want at the end of the day. But we work closely with the supplier to do most of the machining work. I always like to start with hand calcs. So on the left-hand side is a very simple hand calc for bending moment and max deflection. And then I did a quick simulation just to check that what I'm getting with hand is what I'm getting in the analysis, just for a quick sanity check. And now finally onto some simulation. So I used the Apex for the CAD cleanup and for mesh preparations. I could mesh almost the entire structure with hex elements. Since the plates were between 40 and 200 mils thick, I couldn't use shell theory. One thing that was key here is to create groups of sub-assemblies which experience self-contact. So, for example, these areas, they would all be in self-contact or self-touching. So I would make that one group or one contact body. Like, for example, on the fasteners, all the washers would be one contact body, the nuts would be another contact body, the bolts would be another contact body. This just meant that in the setup in market was much faster to set up your contact table. It was also much smaller, and you could find issues much quicker. It saved a huge amount of time. I also used the bolt creation tool. Initially, I thought this was going to be easier than it turned out to be. I didn't speed up this video. This is about how long it takes to do 6 fasteners. We had 334 fasteners. Oops, sorry. Which is fine. It's quite fast if you only have 6 on the page, but as soon as you have 334 in your model, it did really slow things down. So in hindsight, I don't think I would do that again. I'd probably just use RB2's beam elements the more traditional way. But I wanted to try it, and it was a little bit slower than expected. But I must say, once you've done that in Apex, and I think I've now got my head around how to do it efficiently, you can only pull those fasteners into Mark, and then in Mark, it's really quick to set up your preloading and everything else. Okay, so I used RB2s for the M64 fastener constraint, so that's over there, so that I can easily extract the forces. The significant load by far is the clamping load. You can see there 4,500 kilonewtons was the design load, so 450 tons. The operating pressure design is 220, but we're operating at 130. The spindle load is actually quite insignificant compared to the clamping load. Our first machine gave us lots of headaches with not being able to actually sufficiently hold the plates together, and as you would weld, they would separate, and then you have to increase that, but then your boom starts deflecting more, so it also didn't look like this, but we've learned from that machine. So just the difference between design and service loads. Design loads is with the safety factor from the standard built in, and then the service load is what we're actually doing on site. We're also doing something called wave clamping, so basically a clamp pack in front, a clamp pack at the weld, and a clamp pack behind the weld, clamp at 100% pressure, and the others at 60%, and as your weld moves, you change those pressures so that you're not overstressing or over deflecting the structure. Just a bit of a zoomed image of the mesh and also the fasteners. So as I mentioned, 334 fasteners. That was critical to model preload here. So I only did this section of the whole structure, not all the other plates. It was critical because you can't have any relative movement between your splice plates, which are those two plates on the side, one on either side, and your center web. You can't have any relative movement because then you will get excessive deflection and then the process doesn't work. The process is quite sensitive to a lot of deflection because your tool is at about a 2-degree offset. So if you have a boom that's deflecting, your offset's going to change, but your tool's going to stay. Then you're not going to get good bonding. So once this was in Mark, the fasteners were actually quite quick to set up. So once I was done with Apex, I imported the BDF into Mark, and I must say Mark is, I don't want to use the word flawless, but it is really incredible. I really do enjoy it. It's my favorite analysis program by far. There are some quirks, but it is really stable, and reusing an analysis or rerun it, just the setup is really, really great. I could simplify all the contacts to just 2, touching and glued contact, and made the setup a lot easier. Once Girder told me how to do the preload in the specific X direction, that was also straightforward to figure out. There are a lot of elements, as you saw. I think it was 2.5 million for this one. So the contact convergence would make Girder leave this room. But after about 4 days, we got a reasonable result. So this is just the analysis, the result of the deflection. So our design load was 450 tons, so that was what I used here. We had a deformation limit of about 25 millimeters for the process, around about the center there. But one of the process specialists that we work with, he looked at me and said, please keep it below 10 millimeters. So that's what I tried to do. So this is at full load. You'll see just now the results at service loads. We knew that this wasn't going to be a highly stressed platform. Because we're actually more designing for deformation rather than high stresses. So all the stresses were well below 355 MPa, and we used structural steel for it. The mounting rods were critical load-bearing components, as those are the only rods that resist your entire clamp load. With that, also the structure underneath was critical. So one area where there was a high stress initially was in your pin joint, so your pin onto your web. And this just shows how nice it is to use FEA, and you can change the diameter and make the undercut slightly bigger, and then you significantly reduce that force. That stress. So these are the forces from the RB2s over there, which I then used to ensure that the preload of the M64 rods was sufficient, and the reaction forces was used in the civil calculations, which was done by an external company. So it was critical to give them an indication of what those forces are expected to be so that they can design their substructure to withstand our operating loads. Another important part is when you open the latch to take the barrel off, you don't want the whole thing to tip over. That would be very embarrassing. And also I use the analysis to determine a reasonable angle on that latch pin. So that's a tapered pin. If it's too much, it could open the latch while you're applying the clamp loads. If it's too little, you may not catch the boom on the way back up. So in this video, you can see the latch opening and closing on site. It's just sped up, but there it's dropping down. So typically they would drop it down and then they'd remove the barrel out and then they would close it back up again. So the taper angle between that and that needs to be critical, so that when this thing sags down, you can actually catch it. Okay. So on the left, we have a more sophisticated test method. On the right, we have a less sophisticated engineering test method. This was the clamps being activated. So this is from underneath the boom, and you can see, so they all move differently because it's piped in parallel per clamp pack. And then you can see now the load being applied. So there you can see the boom lifting slightly. The video on the right is the latch actually closing, but we use it to measure the deflection. This was just to get an idea of how close was the analysis to the actual results. Okay, so what we can see from the full load deflection, I did not Well, this was for the design load, which was 450 tons, but we're actually operating at 250 tons. So I scaled this down to that, assuming that it's a linear scale. It should be linear. I think it's a fair assumption. And then that is our actual measured load measured deflection with the dial gauge. So that's an error of under 8%, which I think all things considered, all the fasteners not being in, differences in manufacturing and materials, I think that was acceptable. The latch opening one has got a little bit of a bigger difference, but I think we all know what test method was used there, so I think it's understandable. When you see the feet, you can see the scale of this. So this is 200 mil thick plate. It's literally on the catalog, it's the thickest one that you can buy. And we did that both because we didn't want to machine that down to a thinner one, and we needed a really significant piece of steel. But we also wanted to make it a relatively inexpensive component to manufacture, so they could flame cut the outside and only machine what was needed. The center there is the fabricated girder section. So originally this whole part, or the whole machine, was going to be built on site in Worcester. That's why it's made up of so many sections. But in the end, it was actually more feasible to build it up in Joburg and ship the whole thing down. If I knew that from the start, I don't think I would have done it in so many sections. Those are the leg plates. They're 40 mil stick steel. So it's not so easy to pick that up. Oops. Then these are some other components in various states of manufacture. This is my hand next to one of the clamp noses. So there's 100 of these. So once you see this and you see your CAD model, you can quickly appreciate that it's difficult to scale things sometimes from the computer to real life. It was critical for this girder backing to be flat, so underneath here, because your friction stir weld runs along that. So you can't have that thing with big steps or like a sine shape. So we managed to get it within 4 millimeters, which is more than acceptable, considering that there was welding and there was machining on the plates. It would have been ideal to weld or to change the structure a bit and maybe do a big welded structure, but then you'd have to machine that entire bottom to make sure it's flat. And if they were going to do this in Worcester, there's no equipment for that. Then these are our clamp packs. So they were designed for 20-ton loadings. We're running them at 12.5 tons. So they have hydraulic cylinders underneath there, and then linear rails, and then this clamp nose moves up and down. So just an interesting side note, I did an analysis of this whole pack in Mark as well. Originally, we were going to use dovetails for the slides, like you get on milling machines. We wanted to do that because the manufacturer said that it might be up to 7 times cheaper to do that. But after I ran the analysis, we realized that just because of the increase in friction between the linear rail or the linear guide being very low in friction and the dovetail joint, which is essentially steel on steel with grease, so call it 0.2, the load that you have to put in at the bottom is massive compared to if you use linear rails. So the load that you put in here or the force from the pressure is almost the same as at the top here, because this thing is overhung, I think, by about 400 or 500 mils. But if you had to use a dovetail, you can see from the analysis it doesn't work at all. When I remove the friction coefficient, then you get what you put in and what you get out. So then we could know, okay, we can't use dovetails. And also they made a mistake in the quoting, so it actually was more or less the same price. So we just went with this. This is the joy of every engineer. On the left here is just a CAD picture that I just pulled in over a photo, and that's the right, which is the actual product. So it was awesome to see the whole thing coming to life. This was done here in Johannesburg. This is the civil structure. So it's 2 meters deep. It's about 26 meters long, 6 meters wide, about 600 tons of concrete and a lot of steel. On the right there, you can see the M64 threaded rod used to hold this whole thing down. Then this was the day of delivery of the girder, so it was brought on an abnormal truck down from Joburg to Worcester. Unfortunately, I couldn't see it in real life, but this was it being lifted into site so that we can level and position it. So this was the installation of the girder at the facility. So we used these nuts to level the machine, and then we jacked up the machine and dropped the nuts away because we still had to preload afterwards. So then they would throw the last bit of concrete here, with there being a substantial space between this nut and that, so that when you preload, you don't just preload onto the nut at the bottom and not into the structure underneath. That's not your average number 10 socket that you have there. Also not your average torque number. So we used a hydraulic torque multiplier to apply the correct torques based on the preloads that we required. Also a note for if you do CAD designs to, sorry, if you do use CAD designs, put your sockets in your design so you can check where it fits, because you might just make a big mistake somewhere and realize that you can't actually get your socket on, which means you can't preload the component and you can't get a long enough spanner to do it by hand. So this is the welding unit assembly. Hydraulic power pack. It's got an X, Y, Z table, so the X axis moves along the whole machine. The Z is obviously up and down. There's your tool. And the Y is for tracking the seam. So it's got a 6 sensor here, which basically tracks the line when you join the plates together. It seems easy because you're thinking of a thick line, but when two plates are milled and you put them together, you can hardly pick up that edge. So it's just, I think the sensor is around 300,000 Rand, because you really need to pick up exactly that line. And then the sensor at the back is for weld quality, so it does basically a weld profile after the weld, so we can just ensure the quality is as desired. And then we have a camera on there. This is the roller to flatten the two plates joining in front of the weld. And then we have just designed and manufactured. We're going to go install it, I think, next week or the week after. It's just a sander at the back here, so that on their reversing cycle, once they've done the weld, they can actually sand the joint so there's no burrs, and then that can go straight to the next phase. This was a proud moment. I was very relieved to stand next to the machine. I had a moment where it's such a privilege to be able to design something simulated and then actually go and touch the thing there on site and feel this is what it actually looks like. This is the size of it, and it's not so small as you think it is on CAD. This is a video showing them loading a barrel onto the machine. For the closing seam, the latch is opened here, and when you look down the throat there, you can see there's still quite a bit of space just for future products. This is one of the bigger barrels, so we just wanted to leave some space for other product development. On the left here is a typical friction stir weld. The burrs are still on here, so with the sander, the idea is to remove that. So that's the typical finish that you get on a weld. And the other video is just the weld happening with the eNtsa 360 camera on it. So you can see the two plates. This was a test weld, so there's one plate, there's another plate, there's your line. So it just plunged in, and now it's running along there. And now I've just skipped the video, and there you go. This is not live speed yet, maybe one day. But we also included the safety factor so that because when you weld thicker plates, I think we normally welding between 4 and 8 mil, but you could go, say, up to 16 mil, but then your forces become exponentially greater. So we wanted the machine to have capacity because of production as well. They want to increase the feed rates, then your forces are also bigger. This is the final commissioned friction stir welding machine at the GRW facility in Worcester. We did this in collaboration with GRW. If you need a machine built, please chat to me, or designed or simulated or whatever. We will love to help you. Yeah, that's it. I don't know if there are questions.
Why friction welding and not traditional welding?
So with the joint is a lot better, the integrity of the joint. So that's why they use it on the space or the rockets, like the Falcon rocket. And also you're not melting the material. So it heats up, but it's below melting point. So you don't have such a big stress gradient. So it's better for fatigue life. The joint also looks much nicer, and you have basically non-consumables. So with MIG welding, you'd have the wire and the gas and everything else. But with this, you have a tool that can do a couple of welds, and then you can refurb the tool, and then it can do another few welds. And also your just general quality is better over time. Even though the MIG welding, so they used to do this with MIG welding, but you have more defects than with this weld.
Okay, thank you, Hubert.
Cool.
We appreciate it.
That's a pleasure. Bye, thank you. Thank you.